In the liminal space between consciousness and unconsciousness, your brain performs one of its most remarkable feats, creating entire worlds indistinguishable from what we call reality. Every night, as you drift into sleep, you enter realms where the impossible becomes possible, where you can fly without wings, where deceased loved ones speak again, and where the laws of physics bend to the whims of neural activity. Yet, while immersed in these dreams, rarely do you question their reality. Your dreaming brain accepts floating mountains and talking animals with the same neural circuits that process your waking existence. This phenomenon raises profound questions about perception, consciousness, and the nature of reality itself. How can an organ weighing just 3 pounds create experiences so vivid that they become indistinguishable from waking life? What neural mechanisms enable dreams to fool our most sophisticated reality testing systems? And what does this tell us about the nature of what we call reality during our waking hours? The ability or inability of our brains to distinguish dreams from reality reveals fundamental truths about consciousness that scientists have only begun to unravel. This journey through the neuroscience, psychology, and philosophy of dreaming and perception will challenge your most basic assumptions about how you experience the world. Let us begin with a seemingly simple question. What is reality? Philosophers have debated this for millennia, but neuroscientists offer a more precise definition. Reality is what our brains construct from sensory input. Every sight, sound, smell, taste, and touch is transformed by specialized cells into electrochemical signals that travel along neural pathways to create the seamless experience you call consciousness. Dr. Petra Ramirez, a neurobiologist at the University of California, Berkeley, explains, what we experience as reality is actually the brain's best guess about what exists outside itself. We do not experience the world directly. We experience our brain's model of the world. This fact becomes more extraordinary when we consider that our sensory organs capture only a tiny fraction of available information. Our eyes detect just a sliver of the electromagnetic spectrum, our ears register a limited range of sound frequencies, and our other senses have similar constraints. From this limited data, the brain constructs a coherent model of reality, filling in gaps, making predictions, and sometimes creating illusions. The construction of reality begins with sensory input. When light enters your eyes, it strikes photoreceptor cells in your retina. These cells convert light into electrochemical signals that travel along the optic nerve to the visual cortex at the back of your brain. Similar processes occur with other senses. Sound waves trigger hair cells in your cochlea, aromatic molecules bind to receptors in your nasal epithelium, and so on. But these signals mean nothing until the brain interprets them. Various brain regions process different aspects of sensory information: color, motion, form, spatial relationships, before integrating them into a unified perception. This process happens so rapidly and seamlessly that we experience it as direct perception of reality rather than the elaborate construction it actually is. Vincent Young, a cognitive neuroscientist at MIT, uses the analogy of a film projector. Your brain is not a passive camera that simply records what's out there. It's more like a movie projector that creates reality as you go, making predictions based on past experiences and filling in details where sensory information is incomplete. This predictive nature of perception becomes apparent when we examine optical illusions. Take the classic Kanitsa triangle, a figure where 3 Pac-Man-like shapes are arranged to create the impression of a white triangle that does not actually exist. Your brain fills in the missing information, creating contours where none are present. This demonstrates that perception is not passive reception but active construction. The brain's tendency to fill in gaps extends beyond visual perception. In the McGurk effect, when you watch a video of someone saying one sound like BA, while the audio plays another, like FA, you often perceive a third sound like VA. Your brain integrates the conflicting sensory information into a coherent but inaccurate perception. These perceptual shortcuts serve us well most of the time, allowing us to navigate the world efficiently without processing every bit of sensory data. But they also reveal that what we experience as reality is a constructed model, not a perfect representation of the world. If waking perception is an active construction rather than passive reception, then dreams represent the same process operating without external sensory input. During rapid eye movement, REM, sleep, when most vivid dreaming occurs, the brain generates its own activity patterns similar to those it produces when processing external stimuli. In 2013, researchers at the Max Planck Institute for Human Cognitive and Brain Sciences used functional magnetic resonance imaging (fMRI) to scan the brains of sleeping subjects. They found that during REM sleep, the visual cortex activates in patterns similar to those observed during waking visual perception. The same neural machinery that processes sensory input when awake continues working during dreams, but instead of external stimuli, it processes internally generated signals. Dr. Robert Stickgold of Harvard Medical School explains, from the perspective of your visual cortex, there is little difference between seeing something while awake and seeing something in a dream. The same neural circuits are activated in both cases. This explains why dreams can feel so real. They engage the same neural machinery that constructs your waking reality. The sensory experience of dreaming is generated by the same brain regions that interpret sensory input during wakefulness. When you see a mountain in a dream, your visual cortex activates in patterns similar to those it would produce if you were actually looking at a mountain. Yet dreams differ from waking perception in crucial ways. During REM sleep, the prefrontal cortex, responsible for logical reasoning, planning, and critical thinking, becomes less active. Simultaneously, the limbic system, associated with emotions and memory, increases its activity. This shift in brain activity helps explain why dreams often contain illogical elements that we accept without question. In 1976, Harvard psychiatrist J. Allen Hobson proposed the activation synthesis hypothesis to explain dreaming. According to this theory, dreams result from the brain's attempt to make sense of random neural firing that occurs during sleep. The brain synthesizes a narrative to explain this activation, creating the dream experience. While later research has shown that dreams are not as random as Hobson initially suggested, the basic insight remains valuable. Dreams represent the brain's attempt to create meaning from internal activity, just as waking perception represents its attempt to create meaning from external stimuli. The neurotransmitter chemistry of the sleeping brain also differs significantly from its waking state. During REM sleep, levels of norepinephrine, serotonin, and histamine, neurotransmitters that help maintain attention and reality testing, drop dramatically. Meanwhile, acetylcholine levels increase, promoting the internal focus characteristic of dreaming. This chemical environment creates conditions where the brain accepts improbable scenarios without the critical evaluation it would apply during wakefulness. You can have a conversation with a deceased grandparent or fly over your childhood home without questioning these impossibilities because the neurochemical systems that would normally flag such experiences as implausible are temporarily offline. The parallelism between dreaming and waking perception extends to the neural mechanisms of memory formation. When you recall a vivid dream, you access memories formed by the same hippocampal processes that encode waking experiences. The hippocampus, crucial for converting short-term memories into long-term ones, remains active during REM sleep, which is why some dreams can be remembered in detail upon waking. However, the disrupted communication between the hippocampus and prefrontal cortex during sleep explains why most dreams are forgotten. Without proper encoding by the prefrontal cortex, dream memories often fade within minutes of waking unless consciously rehearsed or recorded. The boundary between dreaming and waking states is not always clear-cut. Phenomena like hypnagogic hallucinations, perceptual experiences occurring as one falls asleep, and hypnopompic hallucinations, those occurring as one wakes up, represent intermediate states where elements of dreaming intrude into wakefulness. Sleep paralysis, experienced by up to 40% of people at least once in their lives, occurs when the muscle atonia paralysis of REM sleep persists into wakefulness. During these episodes, individuals may experience vivid hallucinations while fully conscious but unable to move, often leading to terrifying sensations of supernatural presences or malevolent entities. These liminal experiences suggest that the distinction between dreaming and waking consciousness exists on a spectrum rather than as a binary. The brain's capacity to generate compelling perceptual experiences independent of sensory input does not switch off completely during wakefulness. It merely operates under different constraints. Lucid dreaming, the state of becoming aware that one is dreaming while still in the dream, offers further evidence that the neural machinery of dreaming and waking consciousness overlaps substantially. During lucid dreams, the prefrontal cortex partially reactivates, allowing for critical awareness and decision-making within the dream state. In 2009, a groundbreaking study by researchers at the Neurological Laboratory in Frankfurt used EEG and fMRI to confirm that lucid dreaming represents a hybrid state with elements of both REM sleep and wakefulness. Subjects were able to signal to researchers that they had become lucid by moving their eyes in predetermined patterns, demonstrating conscious control within the dream state. This ability to recognize a dream as a dream while still experiencing it vividly contradicts our intuitive assumption that reality and dreams are entirely separate categories of experience. If the brain can simultaneously generate a convincing perceptual world and recognize it as non-real, then the mechanisms that distinguish reality from imagination must be more complex than we typically assume. The phenomenon of false awakenings further blurs the boundary between dreaming and waking. In a false awakening, you dream that you have woken up, often experiencing your normal morning routine in precise detail before eventually waking for real. The convincing nature of these experiences, which can include looking at clocks, brushing teeth, or preparing breakfast, demonstrates how completely the dreaming brain can simulate waking life. Some individuals report multiple false awakenings in sequence, each feeling like a genuine awakening until the next reveals it to be a dream. This recursion of artificial realities raises unsettling questions about how we determine when we are truly awake. If the brain can generate such convincing simulations of wakefulness, what criteria can we use to be certain that our current experience is not itself a dream? The philosopher René Descartes famously wrestled with this problem in the 17th century, noting that there are no certain indications by which we may clearly distinguish wakefulness from sleep. His solution was to find a foundation of certainty in the act of thinking itself. I think, therefore I am. But the phenomenological problem of distinguishing dreams from reality remained unresolved. Modern neuroscience offers more precise ways to frame this ancient philosophical question. If both waking perception and dreams are constructed by the brain, the distinction between them may be one of degree rather than kind. Waking perception is more constrained by sensory input and subject to more rigorous reality testing, but both states involve the brain creating a model of experience rather than directly accessing an objective reality. This insight has profound implications for understanding conditions like schizophrenia, where the boundary between internal and external experiences becomes disrupted. Individuals with schizophrenia often experience hallucinations, perceptions without corresponding external stimuli, that they cannot distinguish from reality. From a neurological perspective, these hallucinations represent a case where the brain's model-building machinery generates perceptual experiences similar to dreams, but during wakefulness and without the recognition that they are internally generated. In 1990, neuropsychologist Dr. Stephen LaBerge conducted research at Stanford University that further illuminated the similarities between dreaming and waking perception. By training subjects to perform specific eye movements upon becoming lucid in dreams, LaBerge demonstrated that the subjective time experienced in dreams closely corresponds to actual elapsed time. A task that takes 10 seconds to perform while awake will take approximately 10 seconds in a dream, suggesting that the neural mechanisms that track time operate similarly in both states. This temporal correspondence hints at deep structural similarities between dreaming and waking cognition. The dreaming brain does not simply produce random imagery and sensations. It constructs a temporally coherent experience with cause and effect relationships similar to those we perceive while awake. The content of dreams further reveals the continuity between sleeping and waking cognition. While dreams often contain fantastical elements, they predominantly incorporate settings, characters, and concerns from waking life. A 2003 study by psychologist William Domhoff at the University of California, Santa Cruz, analyzed thousands of dream reports and found that approximately 75% of dream content reflects ordinary settings and activities, with only a minority featuring bizarre or impossible scenarios. This continuity suggests that dreaming represents an alternative mode of the same consciousness we experience while awake, rather than an entirely separate form of mental activity. The dreaming brain draws on the same memories, concerns, and emotional associations that shape our waking thoughts, though it combines them with fewer constraints. The emotions experienced in dreams provide additional evidence for this continuity. Neuroimaging studies show that emotional reactions in dreams activate the same brain regions, particularly the amygdala and other limbic structures, that process emotions during wakefulness. The fear you feel when chased in a dream engages the same neural circuits as fear experienced while awake. This emotional authenticity explains why dreams can have such powerful psychological effects. A nightmare can leave you shaken for hours after waking, with physiological stress responses, elevated heart rate, increased cortisol levels, heightened vigilance, that persist despite your conscious knowledge that the threatening experience was just a dream. The boundary between dreaming and waking states becomes even more porous when we consider memory and identity. Your sense of self depends on autobiographical memory, the narrative you construct about your life experiences. Dreams become incorporated into this narrative, sometimes as clearly demarcated dream experiences, but often blending imperceptibly with memories of waking events. Studies of false memory formation demonstrate how easily the distinction between dreamed and experienced events can blur. Researchers have repeatedly shown that subjects can be led to remember events that never occurred through suggestion and imagination exercises. If merely imagining an event can create false memories indistinguishable from real ones, dreams, which engage sensory and emotional brain regions more fully than imagination, can have an even more powerful effect on memory. In some cases, people develop persistent uncertainties about whether particular experiences occurred in dreams or in waking life, a phenomenon psychologists call source monitoring errors. These confusions typically involve emotionally significant events or recurrent concerns, further demonstrating the continuity between dreaming and waking cognition. The neural basis for these memory confusions lies in the similar activation patterns produced during dreaming, remembering, and perceiving. When you recall a past event, you partially reactivate the same neural circuits that fired when you initially experienced it. When you dream about an event, similar reactivation occurs. The brain's storage systems do not always clearly tag these experiences as memory, dream, or perception, leading to potential confusions about their origin. The development of virtual reality technology has created new opportunities to study how the brain distinguishes between different types of experiences. Immersive VR can create sensory experiences compelling enough to trigger genuine emotional and physiological responses, increased heart rate during simulated heights, stress reactions during threatening scenarios, and even motion sickness from visual vestibular conflicts. Studies of long-term VR exposure reveal that the brain gradually adapts to these artificial environments, incorporating them into its model of reality. After extended VR sessions, users sometimes report flashbacks, where they momentarily perceive the real world through the lens of the virtual environment, a phenomenon similar to the way dream content can intrude into waking perception. As VR technology becomes more sophisticated, the perceptual gap between virtual and physical reality narrows, raising questions about how the brain categorizes different types of experience. If future VR can perfectly simulate sensory input, the distinction between real and virtual would become purely conceptual rather than perceptual, much as the distinction between dreams and waking currently depends more on context and consistency than on the quality of the experience itself. This technological development parallels the natural conditions of dreaming. Both VR and dreams represent cases where the brain constructs a model of reality based on information that does not come directly from the external world. The key difference is that VR provides artificial sensory input, while dreams generate experiences from internal activity alone. The brain's capacity to be fooled by both dreams and virtual environments stems from its fundamentally predictive nature. Rather than passively recording sensory data, the brain actively predicts what it expects to perceive based on past experience and current context. These predictions shape perception so strongly that when they match incoming sensory data, we often perceive the prediction rather than the actual sensory information. This predictive processing framework, developed by neuroscientist Carl Friston and others since the early 2000s, explains why context so powerfully influences perception. The same visual stimulus can be interpreted differently depending on surrounding cues, an effect demonstrated by countless optical illusions where identical shapes appear different due to their contexts. In dreams, this predictive mechanism operates without the corrective feedback of sensory input. The brain generates predictions about what should happen next based on its models of the world, but without external data to contradict these predictions, they become the entirety of the experienced reality. This explains both the coherence of dreams, they follow certain learned patterns and associations, and their occasional bizarreness, as predictions cascade without external correction. The unreliability of memory further complicates our ability to distinguish dreams from reality. Memory is not a perfect recording but a reconstruction influenced by beliefs, suggestions, and subsequent experiences. Each time you recall an event, you modify the memory slightly, incorporating new information and current perspectives. This reconstructive nature of memory means that over time, the phenomenological distinction between memories of dreams and memories of waking events can fade. Both types of memories become simplified, emotionally filtered versions of the original experiences, making their sources increasingly difficult to distinguish. The phenomenon of déjà vu illustrates another way the brain can confuse different types of experiences. During déjà vu episodes, unfamiliar situations feel eerily familiar, as if being experienced for a second time. Neuroscientists believe this represents a temporary misalignment between perception and memory, where current experiences erroneously activate the brain's familiarity signals. Jamais vu represents the opposite effect. Familiar environments or objects suddenly seem novel or strange. Both phenomena demonstrate how the brain's systems for determining familiarity can malfunction, creating mismatches between objective reality and subjective experience. These temporary glitches in reality processing occur in healthy brains, suggesting that our sense of reality is more fragile and constructed than we typically assume. The solid, consistent world we perceive results from countless neural processes that normally operate invisibly, but occasionally reveal their constructed nature through experiences like déjà vu, illusions, or the hypnagogic states between waking and sleep. The study of how the brain processes time adds another dimension to understanding why dreams and reality can become confusingly similar. Perception of time is not a direct measurement but a construction based on the brain's integration of events and internal pacemaker mechanisms. During dreams, these time perception mechanisms operate differently. Dream experiences can seem to last hours or days while occurring during REM periods of just 20 to 30 minutes. Conversely, complex dream narratives can unfold in the moments before waking, with the brain essentially backdating the experience to create the impression of a longer timeline. This malleability of subjective time occurs in waking life too. During emergencies, time seems to slow down as attention focuses and memory encoding intensifies. During routine activities, hours can seem to pass in minutes when attention is absorbed. The brain's timekeeping mechanisms adapt to cognitive demands and emotional states rather than tracking objective time precisely. The variability of time perception contributes to the challenge of distinguishing dreams from reality after the fact. If memories of both types of experiences contain distorted time information, comparing their durations provides no reliable way to categorize them. Cultural and historical perspectives on dreaming reveal how differently human societies have conceptualized the relationship between dreams and waking reality. Many traditional cultures did not draw a sharp distinction between experiences had while sleeping and those had while awake, considering both equally meaningful and potentially prophetic. Ancient Egyptians believed dreams could reveal divine messages and maintained dream interpreters in their temples. Indigenous Australian traditions incorporate the concept of dreamtime or dreaming, a spiritual realm accessible through dreams but equally real as the physical world. Various shamanic traditions worldwide use dreams as portals to spiritual realms considered as ontologically real as physical reality. The modern scientific perspective that dreams are merely internal brain activity represents a relatively recent cultural development, emerging primarily from Enlightenment rationalism and subsequent materialist approaches to consciousness. This view contrasts with the majority of human cultural history, during which dreams were granted various degrees of reality status. These cultural differences remind us that the categorization of experience into real and not real is partly a social construction rather than a natural fact. Different societies draw the boundary between reality and non-reality in different places, with some including certain types of dreams, visions, or spiritual experiences within the category of real that modern Western science would exclude. The philosophical implications of the brain's inability to fundamentally distinguish dreams from reality extend to basic questions about consciousness itself. If our perception of reality is always a model constructed by the brain rather than direct access to an objective world, then the difference between dreams and waking perception becomes one of reliability and consensus rather than a categorical distinction between real and unreal. This perspective resonates with certain interpretations of quantum physics, particularly the Copenhagen interpretation, which suggests that reality does not exist in a definite state until observed. While it would be overreaching to claim that quantum indeterminacy directly explains consciousness, both fields raise similar questions about the relationship between observation and reality. Philosopher Thomas Metzinger argues that what we experience as reality is actually a transparent self-model created by the brain. Transparent in the sense that we do not recognize it as a model but experience it as reality itself. Dreams represent cases where this model temporarily becomes less transparent, occasionally allowing us to recognize its constructed nature, as in lucid dreams. The recognition that both dreaming and waking consciousness involve reality modeling rather than direct perception has implications for how we understand consciousness disorders. Conditions like schizophrenia, psychosis, and certain types of dementia may represent cases where the brain's reality modeling mechanisms malfunction in specific ways, creating experiences that blend elements of dreaming and waking consciousness. For example, the hallucinations experienced in schizophrenia often share neural mechanisms with dreams but occur during wakefulness. Both involve activation of sensory cortices without corresponding external stimuli, but in schizophrenia, these internally generated perceptions are not recognized as such and are attributed to external sources. Research on psychedelic substances provides additional insights into how the brain distinguishes between different types of experiences. Compounds like psilocybin and LSD alter activity in the default mode network, brain regions active during self-referential thinking and autobiographical memory. This alteration can temporarily dissolve the boundaries between self and world, past and present, reality and imagination. Neuroimaging studies of psychedelic states show increased connectivity between brain regions that normally operate relatively independently. This integration of neural systems may explain why psychedelic experiences can feel more real than everyday reality. They engage more of the brain simultaneously, creating experiences of unusual intensity and significance. Similar neural integration occurs during certain dream states, particularly in REM sleep, when communication between brain regions becomes less constrained by normal waking patterns. This shared neural characteristic may explain why both psychedelic experiences and dreams can generate insights and perspective shifts that persist into waking life. The neural basis for distinguishing reality from imagination involves a network of brain regions including the prefrontal cortex, posterior cingulate, and temporoparietal junction. These areas help tag experiences as self-generated or externally caused, and track the boundaries between self and other, past and present, real and imagined. When these reality monitoring systems function properly, we easily distinguish memories from current perceptions, our thoughts from others' actions, and dreams from waking experiences. When they malfunction due to sleep, drugs, brain injury, or psychiatric conditions, these distinctions blur, creating experiences where internal and external, self and other, real and imagined become confused. Understanding that reality monitoring depends on specific neural systems rather than access to an objective reality challenges philosophical assumptions about knowledge and certainty. If our sense of reality depends on brain mechanisms that can be disrupted or altered, then certainty about the nature of reality becomes a matter of degree rather than an absolute. This perspective has practical implications for understanding anomalous experiences like near-death experiences, out-of-body experiences, and spiritual visions. Rather than dismissing these as merely subjective or accepting them as evidence of supernatural realities, we can understand them as products of reality modeling systems operating under unusual conditions, neither less real nor more real than ordinary perception, but differently real. The study of dreams and consciousness raises profound questions about personal identity and continuity. If the same you exists in dreams and wakefulness, experiencing, deciding, remembering, then consciousness transcends the categories we use to divide experience. The dreaming self and waking self represent different states of the same consciousness rather than fundamentally different entities. This continuity of identity across states of consciousness suggests that what we call self is more fluid and state-dependent than commonly assumed. The person you are while dreaming, with different memories accessible, different cognitive capacities available, and different reality constraints, is both you and not you, challenging simplistic notions of a fixed, singular identity. The relationship between dreaming and creativity further illustrates the continuity between sleeping and waking cognition. Throughout history, artists, scientists, and inventors have reported receiving creative solutions and inspirations in dreams. Dmitry Mendeleev reportedly conceived the periodic table of elements in a dream. August Kekulé claimed to discover the ring structure of benzene after dreaming of a snake biting its own tail. Paul McCartney composed Yesterday, based on a melody he heard in a dream. These creative breakthroughs demonstrate how problem-solving continues during sleep, with the dreaming brain able to form associations and connections that elude waking consciousness. The reduced activity in the prefrontal cortex during REM sleep may actually facilitate certain types of creative thinking by relaxing the constraints of logical reasoning and allowing more remote associations to form. This cognitive continuity extends to emotional processing as well. Dreams often incorporate emotional concerns from waking life, providing a virtual reality where the brain can simulate various scenarios and outcomes. This emotional problem-solving function may explain why dream content frequently reflects current waking concerns, particularly those with strong emotional components. Studies of dream content across cultures reveal both universal patterns and cultural specificity. Certain dream themes, being chased, falling, flying, appearing in public inappropriately dressed, appear across diverse cultures and throughout historical records. These cross-cultural patterns suggest that some aspects of dreaming reflect universal features of human cognition and concerns. At the same time, dream content shows cultural variation in settings, characters, and scenarios. People tend to dream about environments and activities familiar from their waking lives, with cultural technologies and concerns appearing in dreams only after their introduction to a society. Contemporary Americans might dream of smartphones and office work. Traditional hunter-gatherers dream of hunting activities and natural environments. This cultural shaping of dream content further demonstrates the continuity between waking and dreaming consciousness. The dreaming brain draws on memories and concerns from waking life, incorporating culturally specific elements while processing them through universal cognitive mechanisms. The incorporation of waking events into dreams typically follows a nonlinear pattern. Rather than replaying recent experiences directly, dreams often incorporate emotional themes and fragmented elements from the preceding days, combined with older memories and associations. This process, which sleep researchers call day residue, demonstrates how the dreaming brain recombines elements of waking experience rather than simply replaying them. This recombination serves memory consolidation, the process by which short-term memories are integrated into long-term storage. During sleep, the hippocampus replays recent experiences, strengthening some neural connections while weakening others. This selective reinforcement helps extract general patterns from specific experiences, contributing to skill learning and problem-solving. The memory consolidation function of dreaming helps explain why sleep deprivation impairs learning and cognitive performance. Without adequate dream stage sleep, the brain cannot properly integrate new information with existing knowledge structures, leading to deficits in both factual recall and procedural memory. The evolutionary origins of dreaming remain somewhat mysterious, but several theories offer plausible explanations for why this seemingly wasteful activity, creating elaborate experiences during periods of external inactivity, might provide survival advantages. The threat simulation theory, proposed by Finnish psychologist Antti Rauvantuo, suggests that dreams evolved primarily to simulate threatening situations, allowing organisms to rehearse defensive responses in a safe environment. The prevalence of chase and attack themes in dreams across cultures supports this hypothesis, as does the finding that dreams often emphasize negative emotions and threatening scenarios more than waking thought does. An alternative evolutionary hypothesis focuses on social simulation rather than threat response. According to this view, dreams provide opportunities to rehearse social interactions and understand others' perspectives, contributing to the development of social intelligence crucial for success in highly social species like humans. These evolutionary perspectives emphasize the adaptive functions of dreaming rather than treating it as an epiphenomenon or side effect of other brain processes. If dreaming serves specific biological functions rather than merely reflecting random neural activity during sleep, this would explain why the brain invests considerable resources in creating such elaborate experiences during periods of external inactivity. The evolution of consciousness itself may be intimately connected to the capacity for mental simulation demonstrated in dreaming. The ability to create internal models of the world, to simulate possible scenarios, predict outcomes, and imagine alternatives, represents a core feature of human cognition that provides tremendous adaptive advantages. Dreams represent this simulation capacity operating in its purest form, freed from the constraints of current sensory input. The same neural mechanisms that generate dreams likely evolved first for predictive modeling during wakefulness, with dreaming emerging as these predictive models continue to operate during sleep. This perspective suggests that dreaming is not a strange anomaly or evolutionary accident, but a manifestation of the same world modeling capacities that define human consciousness. The brain's inability to fundamentally distinguish dreams from reality reflects the fact that both experiences result from the same reality modeling mechanisms operating under different conditions. The therapeutic use of dreams in various psychological traditions further illustrates their connection to waking cognition and emotional processing. From Freudian psychoanalysis to contemporary dream work approaches, clinicians have recognized that dreams offer unique access to emotional concerns and conflicts that may remain outside awareness during wakefulness. The content of recurrent dreams, in particular, often reflects unresolved emotional issues or ongoing life challenges. Common recurrent themes like being unprepared for an examination, losing teeth, or being unable to locate a bathroom frequently correlate with feelings of anxiety, vulnerability, or lack of control in waking life. By working with dream content in therapeutic contexts, individuals can gain insights into emotional patterns and conflicts that affect their waking function. This practical application of dreams demonstrates their psychological continuity with waking concerns, even as their bizarre elements and narrative discontinuities reflect their different neurological origin. The relationship between dreams and memory raises additional questions about how experiences become incorporated into our sense of self. While most dreams are quickly forgotten, those that are remembered, especially vivid, emotionally charged, or bizarre dreams, can become part of autobiographical memory, influencing our self-narrative just as waking experiences do. In some cases, dream experiences can feel more significant or meaningful than ordinary waking events, leading them to play a disproportionate role in how we understand ourselves and our lives. This phenomenon illustrates how the brain determines significance based on emotional intensity and narrative coherence, rather than the origin of an experience as real or imagined. The scientific study of consciousness continues to grapple with what philosopher David Chalmers called the hard problem, explaining how physical brain processes give rise to subjective experience. The phenomenology of dreaming, how dreams feel from the inside, provides crucial data for this investigation, offering examples of consciousness operating in the absence of external stimuli. By studying how the brain generates the subjective experience of dreaming, researchers gain insights into the neural correlates of consciousness itself. If we can identify the brain mechanisms responsible for creating the subjective experience of a dream landscape or dream character, we move closer to understanding how neural activity translates into conscious experience more generally. This approach treats dreams not as meaningless epiphenomena but as valuable natural experiments in consciousness, cases where the brain generates complete experiential worlds without external input. By comparing the neural correlates of dreamed experiences with those of similar waking experiences, researchers can begin to identify which brain processes are essential for consciousness itself. The implications of understanding dreams extend beyond neuroscience to questions about the nature of reality itself. If both dreaming and waking consciousness involve the brain constructing models rather than directly accessing objective reality, then our confidence in the reality of waking life requires examination. What criteria allow us to distinguish real experiences from dreams, hallucinations, or illusions? Consistency, consensus, and predictability provide practical distinctions, but these pragmatic criteria differ from the philosophical certainty many assume about the reality of their waking experiences. The brain's inability to fundamentally distinguish dreams from reality reminds us that consciousness always involves interpretation and construction, not just during sleep but during every waking moment. The world you experience is not the world as it exists independently but the world as constructed by your brain, a model shaped by evolutionary history, personal experience, cultural context, and current needs. This recognition need not lead to radical skepticism about external reality, but to a more nuanced understanding of perception as an active, constructive process. The external world exists, but we access it only through the models our brains create, models that serve practical functions rather than providing perfect representations. Dreams reveal the creative, constructive nature of the brain's reality modeling systems operating without the constraints of sensory input. By studying how dreams create convincing experiences from internal activity alone, we gain insight into the constructed nature of all experience, challenging the naive assumption that waking perception gives us direct access to objective reality. This perspective suggests that the distinction between dreaming and waking consciousness is not absolute but relative, a matter of degree rather than kind. Both states involve the brain creating models of reality, with waking models more constrained by sensory input and social consensus but no less constructed than the worlds we inhabit while dreaming. Perhaps the most profound implication of understanding why your brain cannot fundamentally distinguish dreams from reality is the recognition that consciousness itself transcends the categories we use to divide experience. The same you exists in dreams and wakefulness, perceiving, feeling, deciding, suggesting that consciousness is more fundamental than the states through which it moves. This continuity of consciousness across different brain states invites us to reconsider what we mean by reality. If the same consciousness can exist in dreams and wakefulness, experiencing joy, fear, wonder, and insight in both states, then perhaps reality is not defined by the origin of an experience but by its significance to the experiencing subject. Dreams remind us that the world we inhabit, whether sleeping or waking, is always partly of our own creation. The line between perception and imagination, between discovering reality and constructing it, proves thinner than we typically assume. In this realization lies both humility about our access to objective truth and wonder at the creative power of consciousness itself.